questions. So our next talk is going to be given by Michael Bluck from Imperial College London. I leave the title here for you to read, but I've got some text, and many of you already know Mike, but I didn't know that Mike has got your degrees in mathematics, and then you've been working in nuclear thermohydraulics ever since I knew you. But anyway, Mike has done a lot of work in nuclear thermohydraulics and also mathematical modeling, and he's the director of the Center for Nuclear Engineering at Imperial College. He's the director of the Rolls-Royce Nuclear Center, deputy director of a doctor training center, and his research is very well funded. I can see from the text we've got here, and he's associate editor of the Journal of Nuclear Engineering and Radiation Science. So over to you, Mike.
Hi, thank you. I assume you can all see my slides. Yes, so I wanted to give an overview really of the work we do at Imperial in coupling, particularly obviously systems codes, which have been mentioned, but subchannel codes and CFD. I won't be going into sort of great detail in any one particular area, but to give you an idea of some of the challenges we've met. Not all of which are particularly technical, it should be said, and I think that's something that has to be borne in mind. So just a brief outline. I'll mention the drivers, issues, and factors in coupling. As I said, these aren't always technical, and I'll just mention sort of the bits about the various codes that we're talking about, or the types of codes more specifically, and then I'll give the body of this will be about some of the experiences we've had in code coupling in various forms, whether that's CFD and systems codes or subchannel codes and systems codes, and in various forms one way or another over a sort of period of a decade really. This particular set of seminars is very interesting. It's interesting to see how far things have come, and in some ways how far things haven't. So first of all, some of the drivers. So clearly the need to model multiscale phenomena from nuclear boiling all the way up to full plant transients is the main driver. There's multiphysics, which has been mentioned. I won't be really talking particularly about that, although there's a multiphysics element a bit later on in a particular implementation. Another driver is there's broad acceptance of lots of existing codes in nuclear. There are very many, and the regulator feels comfortable about these. And as I think Antoine said earlier, that seems to be a good starting point. Nevertheless, it doesn't obviate the need to do lots of validation of what you get. So the issues broadly, there's a lot of legacy codes, and when you're talking about the recent developments, the important nature of legacy codes is often forgotten. They're often proprietary. So the sort of what are quite straightforward adaptations needed scientifically, mathematically, and computationally are very difficult to do in practice. Lack of compatible APIs. You could fill a Scrabble board with the various APIs and protocols that are available. And in this context, there's also a lack of regulator acceptance of CFD, at least in the UK. So the need to couple to CFD is clear. Actually getting the regulator to accept it is another issue. So collectively, those sort of, there's a strong driver to develop code coupling on a number of issues, and so that leads really, in a sense, what follows is really a discussion of the sort of factors that influence code coupling. So firstly, primarily, you've got the constituent codes. They could be proprietary, they could be open source, they could be legacy. In addition to that, there may be accessibility issues. APIs, the application programmer interfaces, again, these could be proprietary, it could be open source, generic, specific, or non-existent at all. Then you've got solution domain choices, and as Antoine pointed out earlier, there's sort of domain decomposition or domain overlapping. I'll be concentrating on domain decomposition as a counterpoint to Antoine's overlapping description. And then there's all the matter of control. Is it a client-server model? Is it asynchronous or synchronous? On the numeric side, is it an explicit algorithm or implicit or semi-implicit? So that's a sort of control issue. And then you've got communications, anything from, and no, it's not dead yet, file I/O, so transfer of information by file I/O, messaging paradigms like MPI or PVM, right down to TCP/IP socket calls. And of course, embodying those are lots of protocols that embody these in one way, shape or form. And the final one, it's just not an exhaustive list, is the mapping between them. Field reconstruction, so profile reconstruction, mapping from a systems code to CFD and so on. And any interpolation of different codes are often dealing with different quantities, and they're not necessarily the same place, and they're not necessarily interpolated in or treated in the same way. So these are sorts of factors, and I'll mention these factors in each of the sort of cases I'll be looking at. So we're covering sort of three broad areas really that encompass broadly the way we treat thermal hydraulics. On the left, we've got systems codes like RELAP 5, Trace, Qatar, etc. So RELAP 5, an example, a two-field model. It has sort of embodied in there lots of regime maps, flow regime maps, correlations, sort of whole component models, and underlying that is essentially a one-dimensional description of the flow, although there are 3D, RELAP 5 3D being an example, but they're not heavily used and they are quite limited. So, systems code is fine for much of the plant, depending on the degree of detail you require, but in the core, it's pretty woeful. Describing the core as 3 pipes or even less. If you need more detail in the core, you look at subchannel codes, for instance, Cobra TF, and so on. And these are sort of more evolved models again, but similarly simplified models of the flow, but they incorporate more detailed models of, in case of Cobra, both of all of liquid, vapor and droplet flow regimes, and additional models to take into account the particular nature of the core. And then on the right, we've got sort of the higher fidelity models, lots of commercial codes, some open source, open foam, code Saturn, etc., embodying the capability to do 3D, RANs, LES, even down to DNS. And so these are important where we really care about the flow detail, and that can be anything from a T-junction, if you like, or flow within sort of tube bundles during transients, as you might see below. So there's a clear sort of range of scales there, and obviously those codes are quite different in nature. So what I'm going to move on to is really a sort of very top level view of some of the things we've done, and this is really a very brief, and I can't say an enormous amount because it's quite proprietary of work we've done with Rolls-Royce, and they're sort of a desire to couple, in this case, subchannel code with a systems code, in particular CTF as a subchannel code and RELAP 5 as the systems code, and you know, the coupling of RELAP 5 in particular has been a long-standing sort of aspect of its development, and in particular it's embodied in terms of coupling using well, they call it an API, it's not really, called R5exec, and so in this context this was an ambition to sort of initially couple these proprietary code like RELAP 5 3D with CTF, very much a legacy code, but accepted as far as the roles and the regulator was concerned. And the API that RELAP 5 3D in principle uses for coupling is R5exec. Again, it's proprietary, and it's a coupling tool based on sort of PVM or variants of, used to accomplish data transfer between the codes. It's not a true API. It's essentially really a scripted control mechanism. And whilst the code manuals will tell you that it can couple with anything, and there's a number of codes there, the requirement here is that these codes have the relevant R5exec hooks in them to communicate using PVM. Notably, these hooks don't exist in CTF, which is a great choice to make, you could say. It's proprietary. The manuals don't tell you what to do or tell you anything about the internals. It just tell you how to script it. You could reverse engineer much of the stuff, but that's very expensive, not least because of the license cost of access to source codes and so on. It's a domain decomposition method. It's synchronous, supports both explicit and semi-implicit communications with PVM, and it maps the thermophysical properties from one to the other, and also maps the flow regime between the two. So this was the issues with R5exec sort of pushed us to go down a different route, really forgetting about the API, the R5exec API, but still following a domain decomposition route with a client-server model and synchronous but explicit. And the communications, it may seem a bit clunky, but we have access to CTF source code, so we can enable communications with MPI into CTF. But with RELAP 5 3D, we actually implemented just a simple file IO and restart mechanism, but again supporting those mappings, the same mappings. So this was quite a sort of clunky thing, just really driven by the selection of the funders' requirements. So this sort of alternative involved data exchange between time-dependent volumes and junctions in RELAP 5 3D and phantom cells in CTF. And depending on the sort of flow direction, we're passing pressure, temperature, mass flow rates of both phases, void fraction one way and pressure, temperature and void fraction the other way. And it was a client-server model, so it had a wrapper, a client written in Python. And as you see on the right, it spawns the wrapper spawns a CTF server and exchanges data with CTF by MPI hooks written into CTF. And using that data from CTF, we adapt the input deck to RELAP 5 3D and spawn a restart. It sounds a bit clunky, but it does work. The there's a need to map the thermophysical quantities because they have different steam tables and thermophysical tables. So that's done by the wrapper. And the output data at each step is written to a PLT file, which is transferred by the wrapper to CTF. So this is a workaround, very much, not as you would possibly want to do it. So validation, verification is important. So this is a verification, and it's a very simple case of a test section and a bypass channel. And in this case, the middle section here is modeled using CTF, and the rest of it is modeled using RELAP. And this is very much a verification process rather than validation, as this system overall is pretty well modeled by CTF and RELAP 5. And the verification process is pretty reliable. The liquid and gas mass flow rates are very well predicted, as you can see. So the possibly one issue is a sort of deviation there for the pressure. I think, as Antoine said, the pressure converges a bit more slowly, but those are small differences. And this is just a verification activity to make sure that things are doing what they should. I won't be able to give any sort of more detailed and more useful verification validation just due to commercial issues. A validation example, which is a PSBT rod bundle benchmark case. It's test series 5 of those considered. It's a bundle 5x5 rod array, uniform axial power distribution. And we're looking at the steady state, and the void fraction is measured at various locations, and it's got a sort of slightly inhomogeneous radial power distribution in that. And all we're doing really is modeling the test section in CTF and the cold leg and the hot leg using RELAP 3D. And the results, I'll go through this quickly, I don't want to go over time. And the results again are pleasing. You can see on the graph on the right the experimental void fraction on the x-axis and the numerical void fraction on the y-axis. There are some outliers. The dotted lines indicate a standard deviation, plus or minus, the variance. And generally the results are plausible and as you can see, good agreement with either CTF standalone or indeed not shown on there, RELAP 5 standalone. So in terms of, it's possibly more verification and validation, all things seem to be working well. As I say, there are issues with the pressure, and we need to look further into that. So that's an example really of coupling in a sort of a fairly clunky way, a subchannel code with a systems code. The next one I'll move on to is coupling RELAP 5 with a CFD code, in this case star CCM. So the constituent code got star, which is obviously proprietary, RELAP 5 again proprietary, and legacy as well. The API used here was at that time, this is 2016, the COSIM API in star CCM. And again, domain decomposition, and it involved a client-server model, synchronous communications. And again, rather like the last case, due to the same reasons broadly, RELAP 5 was on the coupling side was done via file IO and a restart. So comms are through the COSIM API on the star CCM side and file IO on the RELAP 5 side. And there was essentially a wrapper acting as the client, called COWS, COSIM 1D wrapper. And again, the mapping is important for the coupling of CFD, you've got to, going from the CFD to systems code is relatively straightforward. Going in the other direction, you need to recreate the velocity profile. You also, going back from CFD into relap 5, need to make sure that you are consistent in producing the appropriate flow regime map. It's not just a matter of passing those variables. So as an example here, again, a similar PSBT benchmark. The case you can see up on the top right. And so the blue is modeled in relap, and the green, the test section, is modeled here with star CCM. Data exchange depends on, it's a directionally dependent, the data exchange, passing mass flow rate, temperatures, pressures, and so on. This is just for clarity, I've just put the single phase transmissions there. And the control is, as you see here, there's a wrapper essentially around that acts as a client to enable and manage the communications and the mappings from one to the other. Okay, so that was a relap 5 star CCM coupling. Oh, sorry, let me just a different case now, which was the coupling of a systems code again, MHD SYS. So this is a magnetohydrodynamic systems code with open foam. And the advantage here is that in both cases, these were open source and in-house written in terms of MHD SYS. MHD SYS is a magnetohydrodynamic systems code for fusion blanket duct flow applications. It deals with Hartmann type flows, whether it's Shercliffe and Hunt type flows. So the velocity profiles for when the magnetic fields are high are very different to those in normal sort of hydrodynamic cases, including sort of wall jets and so on. So the particular profile reconstruction is very different. MHD SYS also deals with quite heterogeneous heat transfer. You've got, because of the very different flows, you've got very different local Nusselt numbers on different walls of a duct, depending on the orientation of the magnetic field. And you've also got the potential for through wall magnetic field and momentum interactions. So the flow in one duct actually affects the flow in the neighboring duct. Okay, and so these are these sort of various sort of prototype fusion blanket applications. We have flows sort of as a sort of serpentine arrangement. In order to get there, in particular, you often need quite complex manifold arrangements. So whilst the systems code can quite successfully describe the flows in the sort of ducts, the flows within the manifolds are vastly more complicated. So that's the motivation for coupling the systems code to a CFD code, in this case MHD foam. So these are both open source and hence quite generic APIs. It's again a domain decomposition approach, that's synchronous communications, and in this case there's not a lot of data being sent. So we just use TCP/IP sockets. One of the difficulties is most of the significant message passing interface methods are there to pass quite significant amounts of data, sort of high bandwidth, but not necessarily great latency. We're not passing a lot of information, so it's, you know, the opportunity to see what just going right down to socket libraries would do. And as I've said, the mapping is a good deal more complex. for profile reconstruction. And this is essentially on the left, the left of the left picture, if you like, is the MHD sys, and this is the synchronous communications between that and MHD phone. And this is controlled by essentially by the MHD sys acts as the client. MHD phone acts as the client. So this is a case where we have a manifold, so a split from one channel, one duct into three, if you like, and the sort of before and after sort of the junction, the manifold are modeled using the systems code, and the manifold itself is modeled using MHD phone. On the right, you can see the effect that changing, so if you like, before this, on entry, the inlet and outlets, beyond what you can see on those pictures are modeled using MHD sys. And so we're modeling the sort of behavior of the manifold using MHD phone. And you'll see the effect that changing the magnetic, so this is no magnetic field in this lower case, we've got a very significant magnetic field, and it radically changes the flow as one might expect. Okay, so that's really just an application where we have sort of full control, if you like, and full access to codes. And just one sort of final one. Again, this is looking at a sort of, again, the development of interfaces and so on, and various protocols. We're looking at coupling or developing the coupling between star CCM again proprietary, with an in-house sort of open source natural circulation systems code. It's a test bed for dealing with situations that most systems codes don't deal very well with, surprisingly, which is sort of low flow rate natural circulation. And so again, that's written in-house. What we're particularly interested in is deploying the functional mock-up interface API that Star CCM relatively recently incorporated, the FMU, FMI, and there's a link there to it. So it's open source. Again, a domain decomposition. It's a client-server model, again explicit, with Star being the client. And the communications are all managed through the FMU protocol. Again, we'll look at profile reconstruction, flow regime mapping. So this is still under development. Really, a lot of what our sort of work has been is looking at how we practically implement in a broad range. So with the release of FMU in Star, that's what we're intending to sort of evaluate, really, as much as anything. So that's still under development. So just to I've just provided a very sort of broad overview of sort of practical elements, really, of and a few cases of outlining sort of the implementation and what effect certain choices make. As I've been said before, you don't get around things. It doesn't get you that far just because you've coupled two accepted codes. You still need to do all the separated integrated effects tests. The proprietary nature of many codes present many practical challenges. So there's very much perhaps a dissociation between what can be done sort of computationally scientifically and what in practice developers need to do. And there is clearly there's lots of coupling, but paradigms and protocols, but there's a lack of a standardization still. So and of course that's made worse by having to incorporate legacy codes and so on. But with that, I'll end. I think I'm almost on time.
Right. Okay. Thanks, Mike. A lot of information there, and it's really interesting. And now, can we just have a couple of questions for Mike? and then naturally we probably will just move to general discussion.
My name is Venkat.
Yeah.
I'm from Liverpool University.
Yeah.
My question is, is there a reason why you have used star CCM for the coupling? Is it better than ANSYS Fluent, or?
There's a little bit of we have a very close relationship with star CCM. It's not surprising it grew out of our department. so again, it's one of those things I'd reiterate and say, often it's practical things like that that can influence the choice of code, and so often it can be because the vendor has made a technology choice.
Okay.
In many ways, Fluent would be easier.
Yeah.
For a bunch of reasons.
And one other question, if I could ask, when you couple CTF, with relab, what parameters have been exchanged between those two codes?
Let me just. It depends on the sort of direction of flow, but pressure, temperature, mass flow rates, and void fraction one way, and pressure and temperature and void fraction the other. Yeah. In part that that's because there's a need to map between the thermophysical quantities. They're using different steam tables, which is annoying. But yeah, so that's what we do.
Thanks, Mike.
No problem.
Mike, just follow that question. So it's nice to see that you actually work on this to begin with. But I suppose my question is, obviously this is sponsored by Rolls-Royce. If you could say, then what is actually the ultimate goal of this work? Is that for modular reactor? Is that for general applications? So
this is work done under the SMR program. Okay. Yeah. I mean, that's partly why I haven't gone beyond broad description of the protocol, because of the commercial sensitivities.
All right. Yeah. All right. Thank you. Okay. So now we could have general discussions or questions for any of the speakers. Also, at the same time, I believe we have got